In this idealized experiment, a cartoon neuronal fiber in extracellular fluid is used to demonstrate the electrical properties of neurons. A stimulating electrode is inserted into the membrane to inject current, and a second recording electrode is inserted to record the change in membrane potential. After injecting positive current into the axon, there is a delayed activation of the voltage response. This delay occurs because the current has to charge the membrane capacitance. Let's examine the electrical circuit basis of this property. The membrane can be modeled as two parallel paths, a capacitance path and a resistance path. Injection of the current can be modeled as a switch to a current source. Initially, more current is channeled to the capacitance branch as the membrane becomes charged. Gradually, more current flows through to the resistance branch. Membrane potential reflects the current that goes through the resistance branch. Its rise is gradual in response to a sharp current pulse. When the current pulse is terminated, the electric charge accumulated in capacitance flows to the resistance branch until the voltage across the capacitance branch returns to baseline. This accounts for the gradual decline of the membrane potential. When we record the membrane potential at two distant sites, we see the change in membrane potential gradually becomes smaller and smaller. Electric signals decline as they pass along the neuronal fiber. The delayed response caused by membrane capacitance, as well as this attenuation across a distance, are referred to as the passive electrical properties of neurons. Let's examine what happens when we give current injections of different magnitudes. If we inject negative currents, the membrane hyperpolarizes, and the magnitude of hyperpolarization is proportional to the magnitude of the injected current. If we now switch to positive currents, the membrane depolarizes, and the magnitude of depolarization is proportional to the magnitude of injected current. However, if the current is sufficiently large that depolarization reaches a threshold, a fraction of the stimuli can produce an action potential. If the injected current exceeds that magnitude, invariably the action potential will be produced. And this property allows electrical signals to propagate faithfully over much larger distances. Because the action potential can regenerate itself as it travels along the axon, there is no more attenuation at these distant points. These action potentials are an active electrical property of neurons.